Hello, friends. We're here today to talk about thermodynamics, the study of the relationship between heat, work, energy, and temperature. Now, all of those words probably sound familiar, but we're going to do some serious groundwork today in order to differentiate them so that we can be very precise when we use them. Now, I always like to start a new unit with a history lesson, and I'm thinking we can go all the way back to the Roman Empire for this one. Lucretius, the philosopher poet, wrote about his experience observing a mote of dust illuminated by a sunbeam. You've probably seen the same thing. You got sunlight coming in through a window, and the dust in the air in the room you're in suddenly becomes visible. Well, he observes this dust fluttering about and quite correctly supposes that it's not moving of its own accord, that the impetus to get it to move comes from invisible atoms of air around it. He imagines these atoms of air as pounding it from all sides, colliding with it and knocking it around. 1,000 years later, this would be supposed as Brownian motion, which is one of the founding things for kinetic molecular theory. Admittedly, Lucretius was probably observing more of like a tumbling motion, which would be more to air currents than proper Brownian motion. But he did write it out in the form of a poem, which we really don't get often enough in science anymore. So, right idea, wrong example, excellent presentation. I think it shakes out. Brownian motion in the modern sense, you could see by putting a piece of glitter in water on a microscope slide. Even better, you could probably do like a piece of pollen or coal dust. But as long as you have a particle that's nice and visible against the water, you should be fine. Let that particle get to the same temperature as the water. Let that water get to the same temperature as your microscope slide. And when all of that has no difference in temperature between it, look at it under your microscope and you will notice that the piece of glitter, the coal dust, the pollen will be moving around, not sitting still like you might expect. It's bouncing around because it is getting beaten against on all sides by jittering water molecules. Why is that water moving though? There's no currents on a microscope slide. There shouldn't be any forces providing some sort of impulse to get it to move. Where does that motion come from? Simply put, it's the temperature. A moment ago, I mentioned kinetic molecular theory. Kinetic molecular theory is a set of 5 assumptions that we use in order to describe the thermodynamic stuff that we're working on right now. It describes the behavior of particles, most specifically in a gas, but it works pretty well for fluids at different scales. So the first idea is that particles move in continuous random motion. So they are constantly wiggling around, zooming around, bouncing around. They don't sit still. The only exception to this would be at absolute zero. Probably. We'll talk about that in a moment. 2, our second assumption. So they're moving around all the time, continuously wiggling. 2, the number of particles in any sample is extremely large. You don't have to worry about sample size being a problem here. So they're always moving. There's a lot of them. And 3, the space between particles is really, really far apart. So there are a lot of them. They are far apart and they're always moving. 4, because they're so far apart, they don't really act on each other at a distance. The electrostatic stuff between them is negligible. The gravitational stuff between them is negligible. You don't have to worry about more or less any action at a distance between those particles that there are a lot of, and they're always moving, and they're very far apart. The fifth and final assumption is that they don't interact at a distance, but they do interact upon collision. If they meet each other, the result will always be a perfectly elastic collision. If you need a reminder, elastic collisions are the bouncy ones where you have both momentum and kinetic energy conserved. So these particles far apart don't interact with any intermolecular forces. They just beat on each other and the walls of their container. Now, think back to Lucretius's dust in the sunbeam. You could imagine that the dust would be happy to obey Newton's first law and just sit there. No motion, remaining at rest. But it's being pounded upon by all sides by air that is required to be in motion because it has a temperature. And temperature is best explained with thermodynamics. So thermodynamics, that's our unit. And our first lesson of the unit is heat, temperature, and energy. Three words that are often used as though they were interchangeable, even though they are definitely not. We'll start with the most familiar of the three, temperature. Temperature is a measure of the kinetic energy associated with that motion of the wiggling particles. With this, we can associate faster motion, vibrations if it's solid, the actual motion of the particle translating if it is liquid or gas. Faster motion of particles will correspond to higher, well, speed is proportional by its square to your kinetic energy. Kinetic energy's average would go up when the value goes up. So your temperature gets higher. So faster vibrations means higher temperature. And therefore, slower motion corresponds to a lower temperature. Ideally, you should be able to lower the temperature and lower the temperature and lower the temperature until it gets to a point where the stuff stops moving entirely. That theoretical point is called absolute zero, or 0 Kelvin, or negative 273.15 degrees Celsius. What would actually happen at absolute zero? Probably the particles would start popping in and out of existence. If you are curious about what I'm talking about, you can look up the Wikipedia article for 0 point energy and fall into that Wikipedia K-hole. The symbol that we're going to use to abbreviate temperature is T, and it's capital. Remember that T and its capital, just to differentiate, lowercase t we're going to use for time, unless it's repeating. Capital T would be for period in the last course you were in, AP1. But in this case, when we're talking about thermodynamics, you see a capital T, just go ahead and associate it with temperature. It'll also help that usually when we're talking about thermodynamics, dynamics meaning change, we'll actually put a delta in front of this. You wouldn't have changing period because all we ever did was simple harmonic motion. So the idea of a period measurement, which is ideally always the same, having a delta in front of it, doesn't sit right. Hopefully that helps alleviate any confusion as you're looking at your equations. Our units for measuring temperature, Kelvin is best. Kelvin, which is not a scale with degrees, you would use a capital K to indicate because it's named after Lord Kelvin. who very famously said right before the discovery of quantum mechanics that physics was over, no discoveries would be made, just finer and finer measurements. Good stuff. But he did at least get a unit named after him. So Lord Kelvin's scale is an absolute scale, which means that there are no negatives. This is really handy when we are doing our math. You don't have to worry about screwing up signs like what used to happen sometimes when we were working with our vectors. 0 Kelvin, the lowest value of Kelvin, is absolute 0. No motion, probably. 273.15 Kelvin is 0 degrees Celsius. The melting or freezing point of water. And we all know that water freezes at 0 degrees and boils at 100. That means that water would boil at 373.15 Kelvin. For another important temperature that might be a little bit less familiar, about 5,200 Kelvin is the surface temperature of the sun. Of course, the sun is a white hot object, so it glows with white light. And in fact, if you could get anything up to this temperature, it'd start to glow white, as long as it was acting like a black body radiator. So if you had a piece of metal that could withstand that temperature without melting, if you got it up to 5,200 Kelvin, it would glow white and give you more or less the same spectrum as the sun, minus the Fraunhofer lines. The other units that we will use are Celsius. Celsius is excellent because the numbers just kind of make sense. 0 and 100 for freezing and boiling. Well, unsurprisingly, it's based on water, where you have 0 to 100, and then it's chopped up into intervals between that, and then it keeps going above and below. So Celsius works really well for that. Fahrenheit and Rankine degrees are situationally appropriate sometimes, where you get Fahrenheit is often said to be really good at describing the temperature of like a room. Like, is it a little too hot? Because admittedly, a degree Fahrenheit is a smaller difference than, say, 1 Kelvin. But I mean, you could describe temperatures either way. You just have to not be decimal averse. Negative 273.15 Kelvin is impossible. I meant to say negative 273.15 Celsius is absolute 0. I already mentioned that 0 Celsius is the freezing point of water up here, so we'll just put is the boiling condensation point of water. And it would be about 5,000 degrees Celsius as the solar surface temperature. If you ever need to convert, you can look to right here, that absolute 0 value. But if you need it spelled out for you, I'll give it to you. Temperature in Kelvin is your temperature in degrees Celsius plus 273.15. If you are just trying to get to like 3 or 2 sig figs, you can get rid of the 0.15. How often are you really using 5 sig figs? But whatever you are going to use as your conversion, you got to commit to it now because the conversion between Celsius and Kelvin is not on your equation sheet. I would just stick with 273.15. It's one of those things like, could you learn G to 8 sig figs? Sure. Could you memorize pi to a bajillion places? Yes. Why? It's more significance than you're ever likely to use, and it seems like a waste of effort. So 273.15 or 273 if you are playing fast and loose. But it is worth noting that 1 Kelvin is the same amount of temperature difference as 1 degree Celsius. They are equivalent in terms of intervals. That means that delta T, a change in temperature, would be the same in degrees Celsius or Kelvin. So if you're working with delta T, you don't have to worry about converting back and forth. If you're just worried about the difference, that's going to be the same in both. Temperature is best visualized on what is called a Maxwell-Boltzmann distribution. A Maxwell-Boltzmann distribution is a graph with a count of particles on the y-axis and either the speed of particles or the kinetic energy of particles on the x. Now, averages tend to, on an xy plot, take a bell curve shape. And that's pretty much what we see in the Maxwell-Boltzmann distributions. Maybe there's a little bit of skew to the higher speeds. So our y-axis is our number of particles. And then our x, we can think of as the speed of particles. I'm not going to get into the weeds of demarcating. So let's say that something is at 100 Kelvin, very cold. Its Maxwell-Boltzmann distribution might look something like that. Usually they tail a little bit off to the right, though. This peak right here, there is a formula that you do not need to know that will allow you to, from where the peak is on this graph, find the temperature. But we're just really looking at the patterns. If you heat that thing up to 1200 Kelvin, your distribution begins to look like this. Notice that the same sample at a higher temperature has many, 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 many more potential speeds that its particles could have. The distribution gets really, really broad as it increases in temperature. So you have fewer particles at any one speed, but you have more possible speeds for your particles at higher temperatures. This is why when you have like a puddle on a sidewalk, it is not likely that the puddle ever reaches the boiling temperature of water. And maybe in Florida or Arizona or something it might, but probably not. Why then does the water eventually evaporate away? We'll look at your distribution. Not all of your stuff is moving fast enough to break those intermolecular forces and escape the evaporation of those water molecules. You can kind of think of it as like a little tiny version of like spaceships going fast enough to go into orbit. But some of them are going fast. Most of them are going slower. And if you were to continue heating it up to maybe like 2500 Kelvin, your distribution gets even broader. So again, this one is all with the same sample, and the difference is the temperature. If we were to look at different samples at the same temperature, it doesn't actually look all that different. So you'd have your number of particles on the y-axis and your speed of particles in the x. Something like diatomic oxygen, the gas what we are breathing and using as we breathe it. Diatomic oxygen would have a distribution somewhere like this. Diatomic nitrogen, which makes up 70%, 78% of our atmosphere. Not too far off in concept, but do notice that it has a broader spread. Now, these, again, same temperature, different gases. So at the same temperature, what's moving around faster on average? Diatomic oxygen or diatomic nitrogen. And you can see clearly you got a lot of speeds available to the nitrogen that less oxygen would be at. Water is often in our atmosphere here in Florida where it's humid all the time. So let's throw it on there. And then helium would be something like this, where it wouldn't necessarily even fit on here. Helium, what's the difference between it and the others on this list? Helium as a gas is extremely light. Remember, temperature is a measure of the average kinetic energy. These all have the same average kinetic energy, right? Well, kinetic energy is 1/2 mv squared. So if we looked at one particular particle, if your mass goes down, your speed has to go up. So it makes sense that the speed of particles would be highest in the lightest of these samples. But temperature is not the only thing at work here. We also have heat energy to concern ourselves with. The idea behind heat energy is that when atoms move and collide, they transfer their energy. Now, particles move more in a hot object. So let's say that you have been in the gym working your ass off, you're sweaty, you're hot, and you step outside and it's cooler outside. Not very likely here in Florida, but maybe in January. So you're hot, you step out into cool air. Your particles are moving around fast, and the air near you is moving around slow. What's easier to hit? A fast moving target or a very slow moving target? Obviously, the slow moving target. So, for that reason, you kind of get this direction of energy transfer. Because slow moving things are easier to hit, you tend to have a transfer of energy from hot to cold. It's kind of a simplified explanation of the direction of entropy. Again, stuff we'll get to later. So particles move more in a hot object. We've established this, but that means that they tend to collide more, giving them more opportunities to transfer their energy and into these easier to hit targets. So you end up with a net transfer of energy from hot to cold. And remember, I can't stress this enough, your collisions are going to be completely elastic. So kinetic energy is conserved in the transfer. None of it goes to waste or turns into sound. You don't hear diatomic oxygen molecules clacking against each other due to their temperature. Heat. Now, notice we've gotten rid of the word energy here. Heat is that transfer. Heat is the transfer of energy between objects due to a difference in temperature. And again, we're talking about like an en masse net transfer. When two things are at the same temperature, there's still collisions. It's just kind of back and forth. Oh, you got some of my energy. I just got hit and got it back. So when you have a difference in temperature, you have this hot to cold net directionality. But if neither is hot nor cold, it's just kind of a stalemate, ping-ponging back and forth. Our symbol for heat, and remember, heat is this transfer idea, shall be Q for quantity of heat. Kind of like how we used quantity of charge with electricity. And our units for measuring amounts of heat are joules, because after all, heat is a transfer of energy. Energy is measured in joules. Named for James Prescott Joule, so you get a capital J when abbreviating it. And remember that a joule is defined as the amount of work done by a 1 Newton force moving something through 1 meter of distance. So joules are also newtons times meters, Newton meters. Heat is transfer. So it would not be correct to say that this sample has 3,000 joules of heat. Heat is gained or lost. You would not say that this sample has 3,000 joules of heat. Instead, you would say that it has 3,000 joules if it's just sitting there by itself, not transferring it, of internal energy. So there's the heat, which is the transfer of internal energy, and internal energy, which is the energy sitting in those particles causing them to wiggle around en masse. These are the two subcategories under heat energy. So we will define heat energy not as the average kinetic energy, because that would be temperature, but the sum of all kinetic energies of the particles in a sample. You can make an argument that internal energy ought to include stuff like the energy potential from the strong nuclear force holding protons together against their repulsion, or it should include the gravitational attraction between the electrons and the nucleus or something, but we're ignoring all of that. In this class, we are just going to assume that the gases are ideal. And in ideal gases, as I said before, we assume that their intermolecular forces, the intermolecular forces, it doesn't affect this. We're not worried about that stuff. So don't bring up nuclear energy, don't bring up electrical energy, just this Brownian motion kinetic energy. The symbol for internal energy that we will use is, again, another one that we are recycling, a capital U. So Q used to mean charge. T used to mean time period. U used to mean, that's right, potential energy. But there's only so many letters we have to work with. And at this point, I think we've exhausted both the Latin and Greek alphabets. Our units for internal energy are, again, joules, because joules measure amounts of energy. A sample can absolutely have 3,000 joules of internal energy. it could transfer some of that, and let's say it gives off 400 joules of heat. So it started with 3,000, it transferred 400 joules of heat. Now it has an internal energy of 2,600 joules. So that's the difference in how you would use those. And earlier I mentioned transfer happening due to a difference in temperature, which means that this is a really good time to bring up the concept of thermal equilibrium. Thermal equilibrium is when the net transfer of heat between two samples in thermal contact, that means that there is a way for heat to get between them, is zero. What does that mean? It means that they are, by definition, at the same temperature. This leads to a super important key concept of this unit. This unit is thermodynamics, and thermodynamics is governed by 3 laws, which are actually 4 laws, because there's 1, 2, 3, and 0. Thermal equilibrium is described as the 0th law of thermodynamics. And the idea of the 0th law of thermodynamics is if sample A, and it's not necessarily always phrased like this, I'm just trying to break it down so it's a little bit easier to follow. If sample A and sample B are in thermal equilibrium with each other, if B is also in thermal equilibrium with a third sample, let's call it C, A must be in thermal equilibrium with that sample as well. So if A is in equilibrium with B and B is in equilibrium with C, then A must be in equilibrium with C. Think of it as kind of the transitive property between these. And what does the transitive property tell you? It tells you when things are equivalent to each other. So my heat is not different than your heat. The kind of take-home point of this is that we can establish temperature for one object and then use it to compare for another, kind of establishing a basis of comparison or relationship. I couldn't say it simpler or better than Maxwell did. All heat is of the same kind. All right, we move on. Let's meditate on this for a moment. Let's think of an example. You've got hot coffee and an ice sculpture. A hot cup of coffee versus a 1-to-1 scale ice sculpture of Joe. So the hot coffee must have a higher temperature than the ice sculpture. That is evident, right? Like ice is cold, low temperature. Coffee is hot, high temperature. But the internal energy of the hot coffee, if you poured that hot coffee onto the human-sized ice sculpture, would our sculpture of Joe melt completely? Of course it wouldn't. You'd barely even melt the part that you poured it on. The internal energy of the ice sculpture is much greater than the internal energy of the hot coffee. You've just got more particles that you have to get up to, even if it's lower speed, that still adds up. Now, heat is transfer. So, by what mechanism does it move from one thing to the other? We've talked about collisions in direct contact, like particle hits particle. And that's probably the easiest one to think about. And that's the one that we're going to do the most thinking about in math with. And that's called conduction. Heat transfers by three mechanisms: conduction with contact, conduction, contact, convection, which is via flows. Think of hot air balloons rise in the air. Why? Because the air is less dense, so it floats. And then radiation, like leaving due to electromagnetic emissions, like the black body I mentioned earlier, or of course the sun. If you feel something is hot and there's heat radiating off of it, that's not conduction or convection. That's radiation. But like I said, we're going to spend the most time talking about conduction, so we'll start there. Conduction is the physical transfer of kinetic energy of particles due to direct contact. So your particles are just beating on each other, as we were talking about a moment ago. Imagine we have a brick of some material separating two chambers of air. So on this side, there is hot air. On this side, there is cold air. So if we have that net transfer from hot to cold, we could expect heat to come into the brick and then leave into the cold stuff on this side of the brick. So this arrow represents our thermal energy transfer. I don't know if you guys can hear that, but it's thundering outside. This is our hot side, so the temperature is hot here. Here's the cold side, so the temperature is cold here. The difference in temperature we would express as the hot minus the cold. What matters for conduction? Well, the biggest one is area of contact. That's arguable, but area in contact, you can like imagine you take a can of soda and you put it in a bowl of ice. If you stick it up straight like this, so that only the bottom of it is in contact with ice, will the heat slowly leach out of it into the bowl of ice? Of course. But you have less of that ice touching it for the collisions of those hot, fast moving particles to have the opportunity to dump their energy into it. If you had it laying lengthwise, you've got a lot more area in contact for the hot particles to hit the cooler particles and transfer their energy away. It makes it easier to do that by just giving more of that opportunity. So area in contact is huge for conduction. From here to here, the thickness of this brick of material is the length of path taken by the heat as it moves. Thicker walls tend to be harder to move through. Longer paths take more time and therefore give you a lower rate of heat transfer, which is why usually these cans are quite thin. Also, it makes the can cheaper to manufacture by requiring less aluminum, but also they cool up or cool down faster. They warm up faster too, but you can use a koozie for that. Why does a koozie slow it down? Doesn't even have to be that much thicker than the aluminum. It's made of a different material, and different materials get hit by heat differently. As we already talked about with oxygen versus helium, different materials with different masses and different intermolecular forces slowing that down get hit by heat differently. And we call that the thermal conductivity constant of that material. Good insulators have a really high value for this. Or excuse me, good conductors have a high value, good insulators have a low value. And how do all of these things put together explain conduction? Well, if we think of the rate of heat passing through over time, heat over time, the relationship would be that our thermal conductivity constant, as I just corrected myself a moment ago, high value is a good conductor. So if this is a good conductor, if its value goes up, we would expect the rate of heat transfer to go up, a direct proportion. So your thermal conductivity constant must be directly proportional to heat transfer rate. Area in contact, we established, would also be directly proportional. And if you have a bigger difference in temperature, your particles hit harder and transfer more energy at once. So your difference in temperature is also directly proportional. But the longer the path, the longer it takes to get through. So we would imagine that the length of path taken is inversely proportional. And we end up with heat is Q, time interval, lowercase t. Thermal conductivity constant, constants of proportionality usually get the letter K, or if you're doing the classic thing, you would use kappa, but we're going to use K. Capital A for area, delta T for difference in temperature, divided by length of path taken. Length of path taken in word problems is usually just listed as the thickness of whatever the container is. But if we tried to use T for thickness, T for time, T for temperature, let's just use L for length, and it'll be a lot less confusing. Speaking of that thermal conductivity constant, I think it's worth exploring a little bit. Thermal conductivity constant. Again, it's just a constant of proportionality. Usually we give K to these. You've been doing that all the way since your first algebra classes. And it is dependent on the material. Again, good insulators like foam or air are going to have very low values for this. Good conductors like metals are going to let that heat absolutely tear through them, and that'll give you a higher value. Our units for the thermal conductivity constant are going to be watts per meter degree Celsius. That's meters times degrees Celsius in the numerator. I just had a brain fart. The denominator is the bottom. Okay, so meters times degrees Celsius in the denominator. Or, of course, you could do watts per meter Kelvin. And watts are, of course, joules per second meter Kelvin, or joules per second meter degree Celsius. A lot of options here. And depending on who writes the question, they've got their favorites. You can always tell the physics professor's preferences by whether they use Celsius or Kelvin, whether they use joules or watts as the numerator. but really it doesn't matter. All four of these mean the exact same thing. It's only when you throw in your metric prefixes like kilo that you're going to have to start pausing to think about it. Higher K, good conductor. There are plenty of charts that you can look up that have the thermal conductivity constants of common materials. We're not going to necessarily worry about that because usually it's given to you in the problem, unless it's like maybe liquid water or something might be something important enough for them to expect you to memorize it. But 9 times out of 10, it's going to be given to you. Lower K, good insulator. And if you can't tell from my handwriting, this K is lowercase like we usually do for constants of proportionality. We've got a new formula. It's time to take it for a test drive. A 5 meter by 6 meter brick wall, 30 centimeters thick, with a thermal conductivity constant of 0.69, nice, watts per meter degree Celsius, separates the inside of a room, 20 degrees Celsius, from the outdoors, 5 degrees Celsius. What is the rate of heat transfer through the wall? Well, one thing to consider before we get started, what direction will the heat go? Well, it always goes from hot to cold. So the heat is going to be lost through the wall to the outside. You can see this in pictures of houses covered in snow. You can usually tell where the living room, where people hang out is, or where the grow operation is in the attic because their snow melts over those parts. The heat escapes through the roof, melting the snow on the outside. And the thermal conductivity constant is given. If we use our 3-bracket method, which of course I suggest, if you forgot it over the summer, or if you're a former student who's still watching this for some reason, maybe you forgot it over the years. But the 3-bracket method is to write the given variables over here, the equation we intend to use over here, and then show our work. So our thermal conductivity constant is our first given, 0.69 watts per meter degree Celsius. The area, 5 by 6 of a brick wall. The brick wall is clearly going to be rectangular in shape in these dimensions, and the area of a rectangle is simply base times height. 6 by 5 is 30 square meters. If you ever forget your area equations, they are listed on one side of your equation sheet. We need the change in temperature, and that is hot minus cold. For us is 15 degrees Celsius, 20 minus 5, delta change. And the length of the path taken is the thickness of the wall at 30 centimeters, which is 0.30 meters. We want to know the rate of heat transfer. Boyles and Gould's, consider for a moment our units. Heat is measured in joules. Temperature is measured in seconds, and joules per second are watts. If you aren't solving for Q or little t, You might as well just combine them. If it's asking for the heat transfer rate, it wants all of this as one. Energy over time is just power, my guy. You could just save 2 letters and a line. Just call it power. And your answer is going to be in watts anyway. So our power is going to be K A delta T divided by L. So our rate of heat transfer, the power involved here is 30 square meters times 0.69 watts per meter degree Celsius times 15 degrees Celsius divided by 0.3 meters. Now keep in mind this meter is in the denominator. So this is denominator meters, denominator meters. Those cancel. No, wait, they don't. Unless we're also looking at these, which are in the numerator. Denominator meters times denominator meters is denominator meters squared. We have numerator meters squared here. That cancels. So we have no meters left to worry about. Here we have denominator degrees Celsius and numerator degrees Celsius. Those cancel, leaving us with just an amount of watts. Always check your units, kids. It'll allow you to avoid making silly mistakes. All that's left after that is to punch all of this into a calculator. And when you punch all of that into your calculator, you should arrive at 1035 watts as your rate of heat leaking through the wall to the outdoors. So that is conduction. I did say that there were 2 other methods, convection and radiation. If you feel like you need more practice on that, there will, of course, be a practice sheet for it. But continuing our, man, I'm all over the place right now. Let me center myself. Continuing our discussion of ways to transfer heat, we had conduction and now convection. Thankfully, you'll be doing very little math with this, but you will need to identify it when you see it. Convection is the transfer of thermal energy from one place to another by flow of matter. Hot air rises, cold air sinks. When the hot air rises, it takes its heat with it, colliding with some of the cold stuff at the top, warming that stuff up. That cold air sinks toward the floor, allowing it to soak up some of the heat on the floor, and then rises and carries it away from the floor. That's what convection is. There are numerous. What the hell is only one? I guess I didn't center myself too well, but there are numerous examples of this. You could imagine a pot of water on a stove. As the water is heated, it rises because it becomes less dense. Less dense things end up with a buoyant force on them in the presence of more dense things in a gravitational field anyway. So that hot air, that hot water rises up toward the surface, and you get bubbles and steam rising off to carry it away. And then it cools down, which causes it to sink and get heated up again, and you've got a nice current of convection in a loop. Current convection loops are 80% of Earth science. Why did the continents move? Because the core of the Earth is hot, and hot rock becomes less dense and rises up to the top. And then the continents are kind of riding the top of that loop, you see that it's got this direction to it. I've drawn it going clockwise. Well, you can imagine that if you had a little boat or something here, it would scoot this way as part of that loop. This happening inside of the Earth scoots our continents around, spreading the Atlantic Ocean wider and wider every year, uh, making the Pacific Ocean smaller and smaller every year. Um, why do we have ocean currents? Convection. Why do we have wind currents? Convection. Uh, when I was in college, there was a girl I had in my biology lab who thought that wind was created by trees because she knew that trees made oxygen. So she thought that wind was just trees like blowing out huge amounts of oxygen at once. It's still pretty funny to me. What actually causes wind is that you've got sunlight coming down in one area, and especially on the ground there, it'll get hot, and then the heat from the ground pummels the air near the ground, causing that air to rise and move. Well, as it rises and moves, you get a kind of a suction from that displacement that pulls air behind it along with it, like opening your door and pulling the air toward you, and papers get sucked off the table. But it creates a suction, and then the air moves in mass. If you have temperature differences, you get wind currents and water currents and rock currents. Speaking of currents in rock, that would be like lava. Well, a lava lamp works by the same principle. Down here in the base of the lava lamp, there's an old school incandescent bulb. Incandescent bulbs are energy inefficient. And where does that inefficient energy get wasted to? As heat. So the blobs of wax at the bottom melt and increase in temperature, becoming more buoyant. And then you end up with a convection current inside of the lava lamp. Radiation is the third way to get heat from one place to another. It is the transfer of thermal energy through the emission of electromagnetic waves. This thing in the lava lamp, this little light bulb, is really, really hot. And because it is so hot, it becomes red hot or white hot. Red hot or white hot implies that because it is so hot, energy is leaving in the form of light, red light, or the whole visible spectrum blending together. When the rainbow hits you in the eye at the same time, you see white. So this thing is radiating out its temperature. It is cooling itself off, getting rid of heat by sending out light. And you actually do the same thing. Uh, Thermal cameras see you. If there was a predator in the room, it would be able to see the infrared light coming out of you. If I had infrared eyes, my classroom, as I scanned, my students would look like bright little light bulbs. So, at least in some sense, all of those kids are bright. But radiation is just letting that heat energy leave in some form of light, be it radio waves, infrared, microwave, visible light, ultraviolet, and in some of the hottest cases, X-rays. Gamma ray radiation due to temperature is extremely rare. That usually has a lot more to do with nuclear reactions or like catastrophic things happening, as opposed to things just being so hot that they're glowing like that. If you look at the sun with a gamma ray telescope, it doesn't show up. There you go. One last thing to close this lesson out. We talked about thermal conductivity constant and how different materials get hit and affected by heat differently. Another way to describe that you might be familiar with from your chemistry class is to talk about specific heat. Before there was the joule of energy, there was the calorie of energy. And that relates to specific heat very well because it was the first unit we had for specific heat. 1 calorie was the amount of energy required to make 1 gram of water increase its temperature by 1 degree Celsius. Boom, there you go. 1 calorie makes 1 gram of water go up by 1 degree Celsius. And then later, the calorie was replaced by stuff that played better with the other metric units. But 1 calorie gets water up a degree Celsius. 1 calorie will get aluminum to go up a few degrees. But it would make something like, I don't know, styrofoam not go up as much at all. So specific heat is the amount of heat required to increase the temperature of, you can do 1 gram or 1 kilogram. 1 kilogram is the base unit. So I'm going to stick with that. It's another thing where you see different people write it differently. Joules per gram degree Celsius or joules per kilogram degree Celsius. Some weirdos even do kilojoules per gram degree Celsius. But just take a look at the units, get them to play well with the ones that you have. And most of the time, they just end up canceling out anyway. Of a material by 1 degree Celsius. And remember that 1 degree Celsius is the same amount of temperature difference as 1 Kelvin. So again, as long as they agree with each other in the problem so that they cancel out where appropriate, you're fine. Specific heat gets the symbol lowercase c, not to be confused with lowercase c for the speed of light. We really need some new letters to drop. Units, as I was just saying, would be joules per kilogram degree Celsius. Or you could do Kelvin, or you could do kilojoules, or regular grams, whatever. As an example, the specific heat of water, 4,180 joules per kilogram degree Celsius. Or if you are thinking about the calorie, 1 calorie is, well, the specific heat of water, rather, would be 1 calorie per gram degree Celsius. To get this into gram degrees would be 4.18 joules per gram degree Celsius. 1 calorie gram degree Celsius versus 4.180 joule gram degree Celsius. The joule is smaller than the calorie by less than a quarter. The specific heat of wood is about 1,700 joule kilogram degrees Celsius. So you see that wood does not require as many joules to get a kilo of it up a degree. It takes more energy to get water to go up in temperature. And now the specific heat of iron, 450 joule kilogram degrees Celsius. Think about this. Air doesn't have a huge specific heat. It's pretty easy to heat air up compared to, say, water. You go out to the beach in May or April. The air is hot because Florida, but the water is going to still be winter temperatures. Why? Because water's specific heat is so high, it's going to take another month of insulation, not with a U, but with an O as in soul, as in solar, insolation, the absorption of solar energy to get enough heat into that water to have it go up in temperature, at least appreciably. Water is an excellent heat sink. Water cooled PCs are a thing for a reason. Metals have very low specific heats. So putting water next to it can suck up a bunch of that heat and bring their temperature down really, really fast. Consider that uh, Florida is not too terribly far off from southern Texas or Arizona or something in latitude, which means that we should be getting the latitude or longitude? Latitude. Yeah, latitude. So the north-south thing. Anyway, we should be getting more or less the same angle of sunlight and therefore the same insolation as those other areas. Arizona gets a lot hotter than Florida. Florida feels hot, but Arizona, Phoenix, or Las Vegas, Nevada, those places get truly hot and they achieve temperatures that are unheard of here. You can complain about Florida all you want, but it is remarkable every time we hit 100 degrees Fahrenheit. That doesn't happen often. We often hang around it, but we don't usually hit it or surpass it. That can't be said for those western areas. And why? They get the same sunlight we do. Why do they go up more in temperature? There's no water. It's a desert. Florida is a peninsula. We're surrounded by water, and that water acts as a heat sink. During the day, our water is absorbing that solar energy without changing much in temperature. At night, it releases that energy because now it's warmer than the air because the air cools off quickly and that heats the air back up. So we have very tiny day-night temperature shifts and reasonably small seasonal temperature shifts. It's not impossible for it to go from 100 degrees Fahrenheit to freezing overnight out west. So the specific heat of water is extremely important. It's one of the things that makes it such a good chemical basis for life as we know it. All of the ways that you regulate your body temperature are pretty much based on getting water in or out. Uh, when people are hot, the first thing that happens is they start to sweat. Sweating is followed by desperate, like fast breathing. What is that doing? Well, maybe you can get rid of a little bit more moisture by exchanging wet breath for dry air. And in emergency situations, the uh, the vomit reflex. People puke as they overheat. Why? Because your stomach contents are going to be mostly water. If you can get rid of a lot of water quickly, you'll cool down a bit faster. And this might be TMI, but I can't be the only person that this happens to. When you're at the gym, do you always get the urge to urinate? I think it's a body temperature regulation thing. But I think gym peeing is a real phenomenon. Like mid workout, you gotta go take a whiz. I can't be the only one, but it totally makes sense when you're thinking about it in terms of the specific heat of water. And that is recorded that I said that. Beginning to rethink my choices. Q, the amount of heat required to make something increase in temperature is related by the mass and the material itself. Or if you don't want to know the heat, but you want to know the change in internal energy, you find out the same thing. Because what does the heat do? It causes a change in internal energy. We'll do an example problem and then button this one up. A styrofoam cup containing 100 grams of water at 90 degrees Celsius has a 30-gram aluminum spoon at 25 degrees placed into it. The spoon and water reach the same temperature at 86 degrees Celsius. So they are originally two different temperatures, so they are not at thermal equilibrium. But if they sit together due to that conduction, because they're in contact with each other, transfer from hot to cold, eventually they will get to thermal equilibrium and the temperature will stop changing because neither is hotter than the other. And that happens at 86 degrees. What is the specific heat of aluminum? In order to answer this, we will have to make some assumptions. What assumptions are we going to need to make in order to use this to answer that? We will need to assume that there is a perfect transfer of energy, that water energy goes into the spoon and nowhere else. How can we assure that there's no transfer to air or to the container? We could pretend it's in a vacuum, so there is no air, and the styrofoam cup, we'll just ignore it. So we have a spoon completely submerged, no heat leaking out of this water other than to this spoon. Now, those are some lofty assumptions, but those are the kinds of things that you have to do in order to make a simple situation fit with a simple formula. You have to ignore the fact that it's actually complex. Those assumptions are pretty well founded. Like it's one of the things such like simple harmonic motion where it's a good enough descriptor for most cases. The only times where you're going to be really violating those assumptions are going to be in FRQs where you have an experimental design. If you have an experimental design for this, it might ask a question like, what are some potential sources of error? The spoon is not completely submerged. The air is sucking up heat. How could you prevent that? Put the spoon further into the water. Do the experiment in a vacuum chamber so that there is no air. Do it in a better insulated cup. Use your Yeti cup instead of the styrofoam cup. But those assumptions are founded. They're completely like fine to work with, but you should be aware of it when you are making those assumptions. Anyway, three bracket method time. We have the mass of water, 100 grams, which is 0.1 kilos. The change in temperature for the water is negative 90 to 86, negative 4 degrees Celsius. And the specific heat of water, we're doing kilograms and degrees Celsius, so we'll do 4180 joules per kilogram degrees Celsius. The specific heat of aluminum is our unknown. The mass of aluminum is 30 grams, which is 0.03 kilograms. And the change in temperature for the aluminum, it goes from 25 to 86. So that is positive 61 degrees Celsius shift. if we assume perfect transfer from water to spoon, the heat that leaves the water is equal to the heat that enters the spoon. Again, assumptions are being made, but so the loss of heat by the water should be equal to the increase in heat of the aluminum. And for both of those, Q is equal to MC delta T. So the loss of heat from the water, which would be mass of the water, 0.100 kilo, 4180 joules per kilogram degree Celsius, -4. You might be thinking, do we need to put that negative there? I mean, just keep track of it because this is negative here. This negative is going to make it positive for when it goes over to the other side. If you want to just do this real quick to find that and then plug it in, whatever. You know that this is going to increase in heat. I trust you at this point in your career to pay attention to the signs well enough to know when a thing should be negative conceptually. A loss ought to be negative. I'm writing it down so that I actually get a positive answer. Like temperature dropped, so that's negative. That's a negative difference. And there is a heat loss, so my amount better be negative. The two negatives are going to give me the positive that I carry over to the aluminum. But that ends up being, let me grab a calculator. I don't have this one pre-worked out. So, you can't see that on the camera anyway. -0.1 times 4180 times -4. 1672 joules, because kilograms and Celsius are in the numerator and the denominator, of heat going from one into the other. Again, assuming a perfect transfer. And then that goes into the aluminum, which had a mass of 30 grams and a unknown specific heat and a temperature difference of 61 degrees Celsius between its original temperature and its new one. So 1672 gets divided by 0.03, and then it gets divided by 61. And we end up with a specific heat of about 913.7 joules per kilogram degree Celsius. This is usually just rounded to 910 joules per kilogram degrees Celsius. Like if you look at most charts of like common specific heats, it's usually listed as 910 for aluminum. All of this is on your practice sheet. If you want more, which you should, familiarize yourself with this, and then we'll move on later in the week to a kind of a micro lesson about states of matter and how heat transfers between different states. Let me stop the share. All right, team. Hopefully this was enlightening. Hopefully this was enough to get you through that sheet. Your first tiny quiz is coming up. And I don't know, maybe rewatch this on 1.5 speed in order to get ready for it. Adios, children.